Hello, so today we are doing this problem called perfect squares, and the problem says we get a positive integer n and we want to find the least number of perfect squares. So let's say, for example, here we have 1, 4, 9, and 16 that sum to n, and this so we want, for example, get the number 12. It can be divided into 4, which is a perfect square because 2 by 2 multiplied by 2 is 4, and we can do that 3 times. We get 4, 8, and then 4, 12. And this is the least number we can make. We can do like 1 plus 1 plus 1 12 times, but that's a lot more. And so the question is asking for the minimum number of perfect square numbers that can sum up to n, basically. For 13, we can just use 4 and 9. That's the minimum we can do, and that will give us 13. So let's think about this problem a little bit. So here, the first thing we can observe is that, okay, so we can think that any number n that we have, so here they said that the perfect square numbers are this. So any n, you can do 1 plus 1 n times. So basically, add 1 n times, and that would be equal to n, right? So we know that worst case, if it doesn't add up to any other number, we know that worst case, the least number is n, right? Because we can just add 1 n times and get the value. But so that's one thing. So how can we, like, from this, how can we go and do brute force, right? So we know that if we, basically what this means is that if, let's say, we have n that can be divided into a1, such that all of these are perfect squares, right? a2, a3. So that means that n is equal to, okay, let's just generalize this a little bit. Let's say this a k, for example. And so that means that n is equal to a2 plus ak, right? So that means that n is equal to basically here, that means that n minus a1 is equal to a2 plus ak. So basically what I'm saying here is that if from this, basically, if we can compute if we can compute the minimum number of squares for this one as a subproblem, then we can find the solution. And basically what this says is that the min number of perfect squares for n is the minimum. So basically we said that the worst case is n, and so it's the minimum of n, which is the worst case if we use just 1, and for n minus 1, right? Because n minus 1 multiplied by 1, that's just a subproblem, right? If we find this, we can do better for this one. So basically what this means is, let's just try all of them, right? Let's just try n minus 1, try n minus 2, try n minus some k. And once we find the minimum for this, keep going up, right? And so just recursively try all use cases. I hope this is a little bit clear, but just try all of them. Try all possible solutions. That's what I'm saying with the brute force case. And so let's code this up. And so first we need our square root value. So basically we are going to try first to see if n itself is square root. So if we have a number like 16, then the least square number is just 1. Because we can just say equal to 16 because that's the solution. So let's try that first. So let's say I is just the square root of n. So we need to import that. Let's just make sure that if we do math, that we can do so that's it. So let's just import math, or from math import square root. And now let's just check if that n itself is a solution. So if this here is equal to n, then that means the solution can be found in just the least number is just 1. Otherwise, start out with the assumption that it's the worst case and try to improve, and try all other possibilities and see if one of them improves. So basically the way to do that is we are going to say, okay, let's take j, and let's take j equal to 1 and try to find better solutions. So let's say j for j in range of 1 and the I plus 1, because why are we doing this? Because let's say if it's I plus 2, or if it's I plus 1 or I plus 2, we know that the multiplication would be like the square of that would be bigger than n, certainly, so no need to try that, right? So we need to try just from square root and below, right? And so we are going to just try all of them, and take the minimum, the one that takes the least number of times, and do that recursively. And so the result we have so far, and just take this and do it for n, since we already decided we are trying for j, so that means we have one less, which is what I said here, n minus a1, which is, in this case here, it's whatever j multiplied by j, so it's n minus j multiplied by j. And this would give us, we can return, at the end we can return res, and we can say plus 1 because of this worst case here, the case where we are just using one solution, basically using just all ones. And so let's try this one. So we have a float. Okay, so we need to do this. We need to do self dot. Okay, so that's probably because of this here. So let me just say, and just use this. Okay, so if we try to submit this, you can see we get time limited exception as soon as we hit the number 15, because this solution actually does a lot of things. This solution, whenever a solution like this recursively and we don't like memorize anything, or we don't, so we will keep doing this. Like for example, sometimes a number would have let's say 9 and so for example for 12, for the number 12, we might do like 8. It's 8 plus, it can be 8 plus 4, right? Because 4 plus 4 here, but at the same time we can also get 4 by doing let's say, or actually let's take so we can do 9, we can do 3 plus, I'm just trying to find a case that has repetitions, so we can plus 2, right? So you can see, for example, a case can be repeated multiple times, and this case also can happen with let's say this is maybe 4, that's better, and this is 9, that's what I meant. Essentially, yeah, it's kind of hard to come up with an example, but essentially there are a lot of repetitions. If we print here for let's make print for n equal to n, so you can see let's just take 12. Okay, so you can see, for example, 1 was repeated 2 times here. You can see 2 repeated 2 times, or even more. We can see, can we see more than another number? So you can see 6 here, but we had also calculated 6 and 5 here, and we calculated 5 here. And yeah, 4 we calculated it here, and we have it again here. So basically there are a lot of repetitions. So whenever you have a brute force where there are a lot of repetitions, we need to right away think about memorization. But first, let's just think about the complexity of this. So this here, whenever you have something that recursively does one recursive call that is 1 time less, then it's at least, then we know that it's at least O of 2 to the power of n. It could be less. We could maybe think about how to find a tighter bound, because here we are doing the square root value. But yeah, it's at least this. It can go up to this, and so this is really bad. Whenever it's to something to the power of something, that's really bad. So we need to improve this. And one hint that tells us how to improve it is when we print the calls, we can see there are a lot of repetitions. So let's just add a memoization table that just saves whatever was calculated before, and we can just reuse that. And so how can we do that? So we can just say, okay, let's just take a memo table like this, and then let's define a subfunction helper that computes for n, where we would put that code in there. And then here we are going to, when we enter here, we are going to check if it's already saved in the memoization table. If it is, then we can just return it, and no need to recompute it. So that means that for the case after, for example, when we calculate this 4, the second time we try to calculate 4 here, we'll just return what was stored before. And so we need to store the result. So here we are going to store for n, the result is 1. Else, since we are not doing a return anymore, we need to here store the result in the memo table, and at the end just return this memo table value. So all we did is we have this hash map, and now instead of just recomputing every time, we check if we calculated it before, we return it. And so we need to call that helper, the value n, to start running it, and let's see if that works. Okay, so you can see here we have the result. Now let's see if, so before it felt on 15, so let's see the case 15. Okay, so it seems like it was pretty quick for 15. It didn't get time limited exception, so let's submit it and see. Okay, so we still have a problem here. Okay, let's see what we did wrong. What did we do wrong? Okay, let's see. That's interesting. Okay, let's print this helper for n and see, and print our memo table content. Okay, this one doesn't help a lot, so let's just put for 12. Okay, yep, so seems like we didn't add actually to our memo table. It's always empty, so we're doing something wrong here. Okay, let's pass it around. Oh yeah, so the problem is, here's the problem. So the problem is I made a mistake here. Instead of calling helper, I'm calling still the old function. So every time it's the initializing this memo table. Yep, sorry. So now let's just print our memo table and see, make sure that it populates values. Okay, so you can see now it fills us up values, and so that we don't recompute them again. Okay, so let's submit it. Okay, so now we fill on a bigger values. That's useful. So let's see how can we improve this. So this is still repeated many times, but it saved a little bit of more time because we do this check. Let's try and improve it. So one way we can improve it is by directly using DP. Whenever we use this memoization, we can directly think of a DP solution. But for a DP solution, we need to think about our base case, our state, and our goal, right? So what is first our goal? Let's just put the goal first here. And so our goal is to find the least number of perfect square numbers. So find the least number, so the min number of perfect squares that sum up of some n, right? That sum up to n. And so this directly hints to us what the state should be. So the state should be some dpi that represent minimum number of perfect square numbers that sum up to n. And so what is also, we need to also, of course, for the dynamic programming solution, we need to find the recurrence relation, right? And so what is our base case? Our base case is for a dp of 0. So what is the minimum number of perfect square that sum up to 0? That's just 0, right? And so what is our recurrence relation? So if we know the dpi, so what is the state that is less than dpi? Like state below dpi that we care about. That's definitely the only thing we care about is summing perfect squares. So that's minus the perfect square that we found. So that would be some value, let's call it j by j. So basically, let's say this ak, which we said here, some ak such that ak is equal to some kind of a sub k is a perfect square. Basically, a k sub k is a perfect square. And so basically this means that, okay, how can we write dpi as a function of dp of I minus some j multiplied by j, right? So it's just, we are looking for the minimum, so we need the minimum of whatever dpi was before and the new dpi, which is, but since we found, this means that we found a perfect square, and so the number of them is +1 because of this one that we already found. And now we are going to try to find the minimum number for the smaller state, the smaller subproblem, right? And so what is the constraint for this j though? This j should have some constraint, because j multiplied by j should be less than I, because if it's not less than I, because if it's not less than I, that will means that this number here would be negative, and that doesn't make sense, right? That's a non-existing state, so we can't go there. And so we have our recurrence relation, we have the base case, we know what should we return. So at the end, what should we return? The goal function here. That's just, since dpi is the minimum number of perfect square that sum up to I, then the minimum number of perfect squares that sum up to n is just dp of n, and so that's what we need to return, right? And so let's code that up then. Let's code exactly that with the dp function. Let me just put this up here. So let's code this DP solution. And so we need DP, but what should we initialize our DP to? We just need any max value, so we can just, because we are doing min, we need any max value. But since we know that we can do like infinity, but even better, we know that the worst case is adding one n times, so we can just initialize them all to n, because that's the max we can have, right? And so this is the range of all of them, right, from I to 0 or to 1, so that's just n plus 1. And our base case, like we said there, so that's DP of 0. And we need to do our recurrence step and go through all i's. So that's kind of DP says go through all I up to n. So since we have the DP state and we want to find this one, so we need to fill the table up until n. And so we are going to do a range from 1 to n plus 1 so that we can get to n. And since DP0 already filled it, no need to go start from 0 here. And so now we're just going to, we know we have DPI, but we know we need to go through all j's here that are less or equal to I, right? So let's start the j from 1. And then while j, because that's our condition here, let's try all these perfect squares basically. So our DP of I is going to be the min of the smaller state, and but the state itself, like whatever best result we have so far from trying another different value of j, and then we add 1. So exactly our recurrence relation that we had here. And at the end we are going to return our goal function that we said, which is DP of I. And that's pretty much it. And so you can see here it's almost the same thing, except here the j values, that's this while loop here, but this I values, like this loop for I, that's done implicitly with the recursion, right? And we end when we equal to n, so we end when we reach this n, which is the end of the for loop iteration. It's just instead of a recursion, it's done in a for loop and a bottom-up approach, starting from I equal to 1, finding a solution and filling the table as we go. And so let's run this. Okay, so we have time limited with 12 even, so that's bad, which means we are doing, yeah, so I forgot to increase the value to increment to j. Yeah, that's bad. Sorry. Okay, so which works for this case. Let's try for 13, for example. Let's try for 100. Oh wow, 100, yeah, 100 itself is a perfect square. Okay, so we still have a limited, so we still have that problem there. Python is pretty slow, so that may be why. Yeah, maybe we can do, instead of going bottom up like this, we can try instead to do, well, that won't work actually. Oh, so yeah, where is the, sorry, where is the j plus 1? Okay, let's just try to submit it like this. Okay, so it falls on a bigger number, but essentially this is the idea for using it with DP. I think in an interview setting, if you do this, you should be fine. But let me try maybe float inf and make it faster, even though it shouldn't. But yeah, it doesn't, but yeah. So this is the, at least this is the DP solution, and you can see here it's the complexity of this is around O(n) squared, so that's not too bad. Now let's try and think about another way to solve this problem. So that was DP and recursion and memorization. Now let's think about another different way, completely different actually. So whenever we have a problem that asks us for a minimum number, such as this one, we need to think, can we model it as a graph? Which is a little bit unusual, but can we model it as a graph? Because if we can, then finding shortest path would solve the problem, right? Because finding a shortest path means finding a minimum number of like a minimum distance to get somewhere. And so how can we think about this problem? So one way to think this through is to say, okay, so let's just model this as a graph, and when we think about this, we need to find how can we determine if two nodes, like how can we determine the edges when we want to model something as a graph, and how to determine the nodes, right? That's essentially what we are working with here. And so in our case, we know that the nodes needs to be the perfect square numbers, because that's all we care about, that are less or equal to n. That's all we care about, right? That's what the problem is about. We are not interested in anything else, and we want to find the least number of them, right? That's sum to n. So basically, we can think this problem is just finding shortest path from 0 to n, such that x and y are connected if their difference is a square, right? Is a perfect square, right? And this we can think about it two ways also, because whenever we have a shortest path, let's say from 0 to n, we can find the shortest path from 0 to n or a shortest path from n down to 0. Both should work fine. And so I'm actually going to try to do it both ways. So first, let's find shortest path from 0 to n. And so that means we are going to use BFS, right? And so let's do the BFS template. And so we need Q for BFS. So we need collections.default.dq. And one thing we need is, since our nodes are just the perfect square numbers, so we need to somehow store the squares so we can determine the neighbors of each node, right? So we need to save the perfect square numbers. So squares, and we are going to say starts out from I equal to n, and we are going to go through while. So we want only the perfect squares less or equal to n. So suffice to do this, and then we are going to do squares append I multiplied by I, and then increase I. And now we need to count the shortest path, so we need to have something that counts the path, or the level, let's call it. So that starts out as 0. And then what do we need? We need to add we want to find from 0 to n. So we need to get the shortest path, so add the start node, which is 0, right? And then we need to have a visited set so that we don't visit a node multiple times, right? So that's a visited array list here. And then we need to do the template BFS. And so BFS, at each time we are going to do it level by level. So that would mean when we get here, we increase our level. But since we are doing it level by level, then that means that we need to go through an entire level first, then go through the while loop to get to the next level. And so for that, we are going to save the size of the queue because we will be adding to the queue, and so the size will change. So we'll need to save the size of the current level beforehand. And then we'll go through the range of size. So this is going through the entire current level. And then what we are going to do is we are just going to do what BFS usually does, which is pop the first element. And here, though, usually what we do is make sure that it's not invisited so that we don't visit something that was visited. But here you usually go through the neighbors, right? Go through neighbors. And usually we have a graph that can give us all the neighbors. But since this is an implicit graph, it's not like we don't have edges beforehand, but we said that our edges are, we determine our edges that are whenever two nodes, their difference is a perfect square. And so we can just go through all the squares, the perfect squares less than n that we have, and check if any of them verify this condition, that's a neighbor, right? And so let's just go through these squares. And so if that square plus the current value that we have in current is equal to n, basically that means we found a neighbor such that that neighbor value plus whatever we collected so far, whatever we have in our queue, is equal to n. That means we reached the destination. And so our shortest path is just level, because if we keep going, we are only going to increase level by more. And so we are only going to have a worse solution. And so we can just stop right here. Since this is with BFS, since we traverse level by level like this, something like this, let's say it's like this, then this level here, if at this level we found a solution, there is no need to go down because that's the shortest path, certainly from the root. Otherwise, so if that's not the case, then what else? If this value here is more than n, so let's say we are here and we found that the value is more than n. If we go down even more, we are going to find values that are even bigger than n, because at each step we add them together. We are going from 0, the smallest value, and at each step we just go bigger. And so that would mean we don't have a solution. Now otherwise, if it's less, then there we need to explore. And so we need to add to the queue. And so we are going to append this sum here so that we can try more, try to go down until we reach n. And then, so you can see we are accumulating the values in the queue. So that's why current here has all the sums of all the perfect squares numbers up until this level. That's essentially it. And when we do this one, we will keep going. And then at the end, if we didn't reach here, we can just return n, because that's the worst case by using 1 plus 1 plus 1 n times. Right. So you can see here what we did is go through the neighbors in an implicit way, without having like a prior graph, but we went through them by implicitly. We took all the perfect squares less than or equal to n, and we checked those that are either at the destination or are valid, and we add them. But if it's no longer a valid path, we can just stop there. There is no need to continue. And so let's run this and see. Yeah, we need to do this. Okay, so it works for that case. Let's run it. Okay, so this solution passes. Great. So you can see BFS was really easy to do because it allowed us with visited set here to skip anything that was visited before. And so if we think about the complexity of this, I think it's at least O of n to the power of something, x. And I think that x should be, since the square roots would probably be in the order of 4 or something. I think it's something like this, but yeah. So it's a lot better than the O of 2 to the power of n that we had before. So yeah, I said before that the first one I'm going to do is shortest path from 0 to n. So let's see now how can we do it the other way around, because that also works. So we can find the shortest path from n down to 0, which also works because that's essentially the same thing. And so how can that one be done? So the only difference is that instead of starting, there are a couple of differences actually. So we are starting from n instead of from 0, right? We are still going to need these to determine the edges in our implicit graph. And we are still going to need this as before. The only difference is that now we are no longer adding. Since we start from n, we want to go down so that we can reach 0, and we want to check 0 here. So actually here, what our next value, instead of before it was this plus, now it's whatever we have so far minus this square value. And then we are going to check if that is 0. That means we reached where we want, right? So if that is 0, then we can just return level. Otherwise, if it's less than 0, that means if we keep going, we are only going to find smaller values. So there is no sense in going down there, and then otherwise we are going to add this next value here, and we are going to need to add. Actually, in my previous solution, I forgot to even add the value to visited, which kind of was a waste, but that's fine. So we can add it here actually. I forgot to do this for the previous solution, but this is necessary. So we append next so that we don't visit again. And you can see the only difference is that we are starting from n. We changed the relation because now we are going down. And when we reach 0, that's where we found the solution. And we know there is no longer a valid path when it's less than 0, because we'll just keep subtracting. And so yeah, that's about it. Okay, so it returns this instead of. Okay, let's just say if current not visited. If actually next is not even visited, then we add it. And let's just keep. So when we reach n, we will break out of the yeah, so let's run this. Okay, let's run it first on 12 and see. So we should return level actually. Yes, so here when we reach 0, I'm returning the current level, but actually this is the next level, so it should be level plus 1. Okay, actually I think I could just add the 0 the position 0 and then let it return +1. Since the next one would be less than 0. Okay, that still doesn't work. Let's see. Okay, how about just return like in all cases? Okay. Okay, actually I think I know now. So here, when we are going down from n, since we are going down from the bigger value, there is no need to wait until we reach 0. As soon as here we find a value that is in the squares, let's say we found n in squares, we can just return it because that's a solution. So the bigger we found a bigger value that is a perfect square, then that's the best we can do, because if we go down, we are only going to find a decomposition that has more perfect squares, right? So here we can just return level here right away, and we probably don't need to do this anymore. So we don't need to do that anymore, and let's see. Actually, I'm doing current here. I should do next. And so if next is less than 0, then we do that. Next is current minus square. That's correct. Can probably skip this because current will already be visited, and we are checking if it's existing square, it's a bigger number, we return it, and then we do the level. That sounds good. Yeah, this sounds good to me. Let's see. Okay, cool. Okay, let's do 12. Okay, submit. Okay, so time limit exceeded. That means probably we are doing more than we should somewhere here. So here, yeah, so yeah, I'm going to stop here so to not make the video long, but you can see that at least it went through a lot of test cases. The one previous one was faster, not sure really why, but essentially here we are doing the exact same thing, except we are going from n to 0, and so we are subtracting. And then when you reach an acceptable level, we like less than 0, we can do better. If we go down, it's only going to be less, and so we break. And we have our implicit graph done here with the use of these squares here, and yeah, that's pretty much it for this problem. And yeah, sorry about the debugging, but yeah, see you next time. Bye.